welcome back to the lecture series of finite volume series. So, if you see, once we plot all these, how it looks like. So, this is how it looks like. This is our phi f tilde, this is our phi. So, our phi f tilde is phi c tilde plus k. So, L and k, these are depends or dependent on various schemes. So, these are dependent on various schemes. Now, as we said, this complete diagram is called the normalized variable diagram or NVD for higher order schemes. Now, what you can see, as we said, once you plot them in this kind of a function, everything will look like a straight line. So, here is your upwind scheme, this is your central scheme, this line quick scheme, this is form scheme, this is second order upwind scheme, and this is what the downwind scheme. So, all the schemes, they are getting a flat straight line, and the meeting point for phi c tilde is half and phi f tilde is 3/4. So, all of them actually pass through that point 0.5 and 0.75. So, except two schemes, two first order scheme, one is upwind scheme which does not pass through this point. So, by 0.5, 0.75, and the downward scheme. These two schemes, they do not pass through that point. Other than that, all other higher order scheme like second order and third order scheme, they pass through that point. So, in fact, it can also be shown that the scheme to be second order accurate, it has to pass through this point. So, other way around, one can think about that any higher order resolution scheme to be at least second order, it has to pass through this point. So, this is a unique point, and in addition to its slope, q is 0.75, then it will be third order accurate. So, this is the point. Now, the upwind scheme is found to be very diffusive, while the downwind scheme is very compressive, or rather this is anti diffusive, and this guy is highly diffusive. So, and therefore, in NVD what we can see that any scheme whose functional relationship is close to the upwind scheme or diffusive, and which one is close to downwind scheme, that would be anti diffusive. So, anything close to this, that scheme would be diffusive scheme, or in NVD anything close to downwind scheme, that can be termed as anti diffusive scheme, or any other scheme which pass through this point, they will at least have second order accurate, and top of that, if we pass through also 0.75, it will become the third order accurate scheme. Now, this higher order scheme, so what we have seen so far, these are having high resolution, that is one important thing. Then this has to be stable, but at the same time, as we have been saying, these become unbounded. Okay. So, you need to overcome this problem of overshoots or undershoots, okay, which is essentially the oscillations near the gradient, and that gives the platform for devising this scheme for high resolution scheme. Now, what one can do, the linear numerical scheme, that is monotone, that can be the most first order accurate. So, what it says that all higher order linear scheme, they are monotonic city preserving. So, one can think about monotonicity preserving, number 1, and that too, the monotonicity preserving scheme, nonlinear limiter function can be used. So, with this understanding, one can actually devise some higher order scheme, and that can be grouped in 2 special categories. So, there are 2 ways one can obtain. In first approach, what one can do, so limited anti-diffusive flux, which is added to a first order upwind scheme in such a way that the resulting scheme is capable of resolving the sharp gradients without oscillation. So, the limited anti-diffusive flux is added to a first order upwind scheme. So, to become non-oscillatory at sharp gradients. So, problem becomes when there is a sharp gradient which is present in the domain. So, there this upwind scheme actually adds so much of diffusion that the results mears out. So, to avoid that, some limited amount of anti-diffusive flux can be, that could be one approach. Other approach, a smoothing diffusive flux is introduced into a higher order unbounded or unbounded higher order scheme. So, the second way is one can actually add some smoothing diffusive flux to a unbounded higher order scheme to restrict or damp out the unphysical oscillations. So, this is how one can actually move forward to have different kind of schemes. Now, due to their multi-step in nature and difficulty in balancing the 2 fluxes, the flux bending technique tend to be very expensive numerically, and this is why here what we will try to do, see something with a limiter kind of approach, and which will give rise to the scheme which belongs to the class of total variational diminishing, that is TVD scheme. So, this is another class of scheme, higher order scheme, which also can capture that sharp gradient, but without introducing. So, essentially it means that you use both the advantage of the property of less diffusion and less dispersion kind of system. So, the composite scheme approach will be discussed, and within the framework of normalized value formulation, and which can be seen in the normalized value diagram. So, first we will discuss about NVF and NVD, and then we move to kind of approach to get this scheme. Now, the point comes the convection boundedness criteria. Boundedness criteria. So, this is an important criteria which needs for devising this kind of higher order scheme. So, the what your numerical scheme is expected to do? It is expected to preserve your physical properties of the phenomena which you are trying to represent or replicate through the numerical approximation. So, the condition that bounded convection scheme should satisfy can best be understood once we start analyzing the physical properties of convection. So, that is what is very important. So, once we analyze the physical properties of convection, then only we can understand this convection boundedness, because that is what it is going to do, which is supposed to represent a physical phenomena through numerical approximation. Now, convection transport fluid properties from upstream to downstream. Typically, convection means it goes from upstream to downstream. That is a standard process. If the gradient is in this direction, the flow moves in this direction. So, the numerical convection scheme should be always upwind biased, or else they will lack the convection stability. So, in addition to value at the nodes which are connecting between your phi c and phi d, these are the nodes which are connecting, the value at the far upwind node which lies at phi u is also important and to be taken into account when devising this kind of things. So, we have already seen in that normalized value framework that the numerical convection scheme is monotone. So, monotonicity is one important property, and which was kind of one can mathematically think about minimum of these phi c and phi d, which is less than your phi f, which is also bounded like maximum of phi c and phi d. So, normalizing the above condition, which will get you minimum of phi c tilde 1 less than equals to phi f tilde, which is max of phi c 1. So, this is called the convection boundedness criteria for implicit steady state flow. Implicit steady state flow, where you get this. Now, also to get this boundedness criteria, we can see in a picture which shows the convection boundedness criteria CBC on an normalized variable diagram. So, which shows the region of phi f tilde. Now, what we can see here, phi f tilde equals to different values. Function of phi c, it could be function of phi c tilde equals to 1. So, when it function of phi c, that means it is continuous. This case it is if phi c tilde equals to 1, that means it is here, then the function of phi c tilde is 1. Other case it could be function of phi c tilde with phi c less than function of phi c less than 1. So, this is the case where phi c tilde lies between 0 to 1. That means, if phi c tilde lies between 0 to 1, or it could be function of phi c tilde which is 0, and that is if phi c tilde is 0. So, if it is 0, then the functional form would be also 0, or it could be phi c tilde equals to phi c tilde, and in this case if phi c tilde less than 0, that means this side, or phi c tilde greater than 1, then this would be always phi c tilde. So, you can see this criteria is quite intuitive and can be also seen in this NBD and with the next picture. So, what happens if we see here? Now, this one, that importantly it shows the values of phi f tilde and convection boundedness criteria. So, this all these three picture shows that, and how one would interpret these things, or what is the physical significance to that. Now, if phi c has a monotonic profile, the interpolation profile at the cell surface should not yield any new extremum. So, thus it is constant by the phi values at the nodes of the connecting faces. So, as the value of phi c get closer to phi d, still it is within the monotonic regime, the phi f will also tend towards phi d, and when, so this is the case when phi c actually will get closer to phi d, the monotonic profile of phi f also close towards the phi d, or the other case when phi c tilde or phi c becomes equals to phi d, phi f also becomes to phi d, which shows this case where this guy goes close to phi d, that means the constant value here, the flat line, this is a monotone profile, that means there is no extremum at C, and the other case it shows that this guy, so this is the regime what we are talking, when it goes close to phi d, phi f also goes close to. So, the condition that phi c tilde and phi f tilde they pass through 1 1. Now, the other case it could be when phi c is greater than 1. So, phi f is assigned the upwind value of phi c. So, this is the case when phi c is greater than 1, then this guy will be assigned a value of phi c. So, this has the effect of yielding the largest conditions or the flow conditions which are actually happening physically in the domain. So, what it tells you that if there is no external physical mechanism to yield the extrema, that is a source term. For example, if there is no external mechanism, then it dies out, the extrema actually dies out. So, a similar mechanism takes place when phi c tilde is less than 0. However, one point you can note here, when phi c get closer, so phi c goes closer to phi u or get closer to phi u coming from the non-monotonic regime, then phi f would be equal to the upwind value phi c until phi c equals to phi u, implying that condition that phi f pass through 0 0. And the other situation where phi c tilde less than 0 or phi c tilde greater than 1, either of these two cases. So, the solution will be in a region where convection is dominant and upwind approximation will be an excellent one. So, this is what one can understand, that what is happening with different scheme. Now, we can devise the high resolution scheme. So, the high resolution scheme, the monotonic profile range. So, the monotonic profile range is phi c tilde is between 0 to 1 and it pass through 0 0 and 1 1, while the remaining with the upper triangular region in this particular picture. If you see in this particular picture, this upper triangular region, so on the NVD. So, on the other hand, in non-monotonic region, so non-monotonic region or range would be phi c tilde less than 0 or and or phi c tilde greater than 1. So, this is a non-monotonic range and the monotonic range is 0 to 1. So, these are already shown or we have seen in the normalized variable diagram, and in that case when it is in monotonic range, they need to, any scheme they need to pass through these coordinates of. So, now there are number of well known high resolution schemes which can be built in this particular fashion, and they can be also seen graphically how would they look like. So, what is essential is that we need an improved convergence behavior. So, that is what is required from this high resolution scheme. So, the HR scheme should avoid any hard. So, HR scheme, to have these HR schemes must avoid hard angles and its profile connection point as well as its horizontal and vertical profiles. For example, if we consider some scheme, the SMART scheme, this we will talk about that how it is devised, or squeeze scheme, the converge or quick scheme, the convection or the convergence can be substantially improved by a minor modification to the vertical portion of its profile, such that if someone uses this equals to 3 phi c like that, in the region where phi c tilde is 1/6 to 0. Similarly, so those changes one can see in those different, how they actually improve. So, for example, if you use the mean mode kind of scheme, mean mode kind of scheme. In that case the phi f equals to, it becomes 3 by 2 phi c, when phi c lies between half and 0, it will become half phi c tilde plus half. If it lies between half and 1 and other places it is elsewhere, it is phi c tilde. So, this is the behavior of the mean mode system. So, one can see that how this is the mean mode. Now, again these are the pictures which shows, this is again normalized variable diagram for different HR schemes. So, one case we can see that the mean mode case, where we have seen that it is the phase value is 3 by 2 phi c, when the phi c tilde lies between 0 to half. That means 0 to half the phase value is 3 by 2, when it is between half to 1 it is half phi c plus half, and elsewhere it is all phi c. So, that is what the mean mode operator does. Similarly, if we go to bounded CD, so bounded CD shows that phi f equals to half phi c plus half if phi c tilde lies between 1 and 0, or elsewhere it is always phi c. So, if you see in the NVD, this is what the bounded CD does. So, it says between 0 to 1 it is half, that is a constant value which is sitting at the phi f plus phi c, how it varies, and other than 0 to 1 the value is always phi c, which goes as a linear profile. So, in the NVD if you look at it, then similarly this scheme OSHAR, that is another higher order scheme. The OSHAR says that phi f equals to 3 by 2 phi c if phi c tilde lies between 2 by 3 and 0. So, that means phi c tilde lies between 0 and 2 by 3. So, which is somewhere here, it is only 3 by 2 phi c, and then it becomes 1 if phi c tilde lies between 1 to 2 by 3 and elsewhere it is phi c tilde. So, when it is 3 by 2 by 3 and 1, this is always 1, that is the constant value. So, you can see this is the point which is 2 by 3, before that it was 3 by 2 phi c, there is a slope, and then beyond that it all phi c. That is how the behavior of the OSHAR scheme. Now, the smart scheme, if you see here, the smart has phi f equals to 3 by 4 phi c tilde and plus 3 by 8 if phi c tilde lies between 5 by 6 and 0, that means 0 to 5 by 6, 0 and 5 by 6, which would be somewhere here, which is 3 by 4, a 3 by 8 constant, but then the slope is, so this is the point which is 5 by 6, and if phi c tilde less than 1 between 5 by 6 it is 1. So, here beyond that to 1 it is constant value, and then you can see it is always phi c where elsewhere. So, this is another high resolution scheme which shows up to 5 by 6 this point, the profile follows some linear combinations. This is already we have said that all these schemes they can be, the functional values of phi a would be represented at a function with some combinations of the linear system which is L, and so it can be represented at L phi c tilde plus k, and this k and L value are different for different profile. As we see, the SMART scheme provides this kind of profile, when OSAR scheme provide this kind of. Now there are others one also there like muscle, STOIC and all these we will see, but the point is all this higher order scheme belongs to this kind of profile definition or the normalized flux definition with some factor constant with phi c plus constant, and that is how we are building all this. And now we will stop here today, and the other scheme we will see in the next lecture. Thank you.